Hello and welcome to this video on water hardness. Water hardness has been a concern this summer, with the local town water supply surprisingly high in salts and minerals. This has had an effect on many things. The water hardness has had a particularly noticeable effect on brewing. First things are to define water hardness. Water hardness in common usage is the general term for a noticeable concentration of salts and minerals in water. In stricter technical usage, the term refers to a range of only mineral content in water, differentiating this into a range from soft to very hard. The USA's Department of Environmental Protection has given this two categories. The primary standards have regards to health and safety issues. The secondary standards regard taste, odor, color, and corrosion. The two major contributors to water hardness are magnesium and calcium. This can be seen in a film on glass after it has been washed. This is the deposits of the dissolved and then precipitated minerals after they have reacted to the detergent. These are also stereotyped by the abandoned locations where rusty pipes have scale building up on them. The local water supply is contaminated with these minerals as the municipality substitutes the water supply with both bore water and aquifer water supplies during periods of drought. As a result, this problem tends to ebb and flow, with the worst of it occurring during periods of drought or when rainfall is just low. This makes sense as both the bore water and aquifers pass through rock and sediment layers, either as the water sinks into the ground or as it is drawn out. As this is added to the larger supply, it is diluted, and as the main supply drops, it is either a smaller dilution or greater after rainfall. This is further impacted by the municipality regularly conducting a cleaning process. This alters the chemical composition slightly. This is generally a minor pH change. It is noticeable in the kettle where the water is boiled and heavier water leaves a residue. This water is generally in the category of very hard at its worst, and this is in the range of 500 micrograms a litre. By comparison, saline is about 5 grams a litre, or 10 times that level. On average, it is 100 to 200 parts per million, which is generally considered moderately hard to very hard. There are no recognized health concerns to hard water, and there may be health benefits by contributing to bone and teeth mineral requirements. This environment of high concentration minerals creates an environment in which there is a surprising availability of free electrons. This is largely from the calcium and magnesium both having a 2+ charge, which means there are 2 electrons in the outer shell, which can break off or interact with other chemicals. Hard water has an established history in brewing. It has been recognized by Japanese sake brewers in the 19th century, where it altered the quality of sake brewed between the same brewery operating in different locations. It is recognized by the beer breweries of different cities, and this can often be a defining feature of the beer produced. There is a link to this in the description box below. These fermentations have been behaving oddly with stalled fermentations and inconsistent results. This has been traced to the water used. This raises the question of why, and more importantly, how. Evidence from whiskey fermenters and distillers show that the ions in the hard water directly interfere with the fermentation. An example of this is in Scottish Highland waters. The hard water reduces the viability of lactic acid bacteria to grow. This water is harder, and the effect it has is to lighten the spirit. Each of the possible minerals contributing to water hardness works in a unique way, and these are some of them. First is calcium. Calcium affects enzyme activity and yeast flocculation, the latter of which has been covered already. This is probably the most significant factor in brewing. This should increase the longevity of yeast enzymes and therefore the effective range of pH, and time for which can work. This leads to greater fermentation. Calcium has another useful aspect. It depresses the fermentation pH as a beer mash is boiled and the calcium precipitates out. This may explain how the Highland water is more useful in whiskey production. This is not as useful in fermenting for pure ethanol. However, yeast has been shown to have greater flocculation when exposed to free calcium in a wash. This would have the opposite effect if the calcium levels exceed that used by the yeast for normal function. Calcium should be in the range of 50 to 150 parts per million for brewing, but to this effect, the most common range of calcium at the moment is somewhere around the range of 224 parts per million in the local water supply. This is considerably higher than that desired, and on a regular basis it can be far more than that. The next is magnesium, and this provides a sour taste as it is a metal and it is also highly reactive. This incorporates in most enzymes as a cofactor for function. The reactive metal species causes conformational changes in these enzymes. This either makes them functional or deactivated. The recommendation is generally that brewing water should have 0 to 30 parts per million of magnesium. However, the local water has an average of 125 parts per million. This has a substantial effect on the water supply and how viable and reliable it is to use, without other actions being taken. Next is sodium. At low levels, sodium has a sweet taste effect. At higher concentrations, sodium has a salty taste. This is for the rather obvious reason that it is 1/2 of the sodium chloride compound, better known as table salt. Sodium at moderate levels has no significant effect on yeast performance, but this changes with the concentration gradient. Yeast has a native amount of sodium inside the cell. This amount keeps it in equilibrium with the environment. As the environment outside the cell rises, it has an effect on the amount of osmotic pressure on the cell. If the sodium gradient keeps shifting, it may cause the cell to suffer from osmosis. This is the movement of water from inside the cell to outside the cell in order to balance the gradient, or at least in an effort to do so. If this continues, the cell may lyse due to damage. It is recommended that sodium be between 0 and 75 parts per million. However, the local water is at somewhere along the lines of 224 parts per million. This is considerably above the range desired. Next is carbonate. Carbonate covers a combination of carbonate, being carbon and 3 oxygens, or bicarbonate, which is hydrogen, carbon, and 3 oxygens. Normally this is matched with a sodium element to it. This has the effect of depressing the fermentation pH. This is done by the release of a hydroxyl group when the carbonate interacts with water or other compounds. The presence of carbonate ions and their effect in raising pH can result in less fermentable sugars, in other words, a high dextrin or maltose ratio. This leads to another increase in pH, and that is twice that of calcium's pH reducing effect. This can be seen in carbonated drinks. The sweetness of the carbonated drink is countered by the high pH, which is an alkaline solution. It's generally recommended that for brewing, carbonate should be at about 20 parts per million. The local water has similar levels of carbonate as it has sodium. At these levels, it creates a notably harsh edge to the water. Next are the chlorides. Chlorides cover a range of chlorine-based structures. These are added as a disinfectant. Obviously, a disinfectant is a problem when the idea is to grow and maintain a microbe, particularly yeast, in it. These chlorides can be removed from the water via different approaches, including aeration and boiling. These particular compounds are largely volatile. However, there are chloride molecules which are not as volatile and not readily removed. Chloramine is an example of this. It will not conveniently boil out, but will require an extended period of high heat. It can be done so over a long period of time when exposed to air, this being somewhere in the 48 to 72 hour range. It is recommended that chlorine not exceed 40 parts per million for brewing. Local water has a level that is similar to the sodium and carbonate levels. This is 6 to 7 times what should be expected and used for brewing. Next are the sulfates. Sulfate is highly soluble in water and it is highly ionic. This highly reactive element makes water permanently hard and is very difficult to remove. Sulfate has an interesting quirk in how it accentuates the bitter taste of hops. At levels over 750 parts per million, it can cause diarrhea in humans, and it is recommended that sulfate not exceed the 150 to 200 parts per million range for brewing. Sulfates positively affect protein and starch degradation. This will then favor the production of a mash and then the sedimentation of the yeast and the yeast waste products. This is a good thing if you can keep the sulfate level below this. The combination of sodium, which has a high concentration of sulfate ions normally, will generate a very harsh bitterness in most brews. Therefore, sulfate should be kept between 150 and 350 parts per million for brewing. This will ensure the home brew is both tasty, stable, and unlikely to turn sour anytime in the near future. Sulfate is measured in the same sample as calcium with the local water authority, and this puts it at roughly 224 parts per million. This is well above the bottom of the range, but maybe within the middle of the range, depending upon how high the sulfate level rises to during periods of peak presence. Finally, there are the metals. In the local water supply, particularly noticeable are the iron salts. These have a negative action at anything above 0.2 milligrams in a litre. This prevents a complete saccharification, which is conversion of sugars from complex to simple, and therefore being usable by the yeast. This results in a considerable amount of cloudiness in anything you are trying to brew. It also hampers the ability of the yeast to function properly. Next are the copper ions and salts. These can occur in very low concentrations, but it also only takes roughly 100 milligrams per litre to have the desirable effect. Anything above this and it interferes considerably with yeast function. At levels above 10 milligrams per litre for yeast, it can be very toxic. Finally, there is zinc, and this is an important component for yeast function in a normal way. It has an effect on protein synthesis and on yeast growth. It also imparts and impacts on the ability to flocculate and stabilize foam. Direct testing of water as it reaches the tap here has reached salt and mineral levels of 500 parts per million. This has an adverse effect on the viability of fermentations. It has caused a large number to stall and has reduced the viability of yeast by increasing flocculation, decreasing enzyme activity, and creating other problems. If you cannot measure water directly, most water authorities hold detailed records of the water hardness. This may be tested monthly, biannually, or annually. This can be accessed via their website or directly contacting them. If you do not have the option of taking up an alternative water supply, you can address hard water by distilling it from the tap. This will need to be rebalanced with minerals and salts, and often this is done with Epsom salts. There are guides available online. As a final note, parts per million can be converted as a 1-to-1 ratio of parts per million to milligrams. For every 1 part per million, it is 1 milligram. Thank you for watching. Please post any questions, comments, or suggestions you may have below.